right? So finite element modeling in two-dimensional. So when we talk about finite element modeling, so it's basically is more towards we how we visualize, or how we look into the problems of our actual system, or here how the interaction of physical interaction of the actual models, our actual system are taken in place. So the task, I mean the what we call the challenge here in finite element modeling is more towards understanding this physical behavior. So a lot of times, okay, we have to deal with how to interpret, particularly on understanding what we call its boundary condition, how the actual model or actual systems being interact physically. So we would want to translate these interactions uh, into our finite element modeling. So that become a real challenge for if you are looking into these areas. So matching the appropriate finite element to the physical behavior, basically it's one of the challenge. So we would want to, because we are already in approximation under this finite element analysis method, is a numerical approximation. So we will want to get as close as to the actual or exact solution. In this case, here the most challenging part is how to match this particular finite element model to the actual physical behaviors. So that is one of the challenge on finite element modeling. So what we can do is we try to minimize, or I mean, beside looking into the context, the boundary conditions, so the meshing itself also we have to, because it's about discretization. Finite element analysis is about discretization into elements, nodes. Then we solve it, right? So meshing itself, or your element itself, is one of the consideration that would help us to get as close as to the actual solutions, actual problem. Okay, so the aspect ratio of the elements is one of the consideration that you have to take notes. So aspect ratio basically is the ratio of your longest dimensions of your element to the shortest dimension of your elements. So if it's large, okay, your aspect ratio is large, basically it will induce inaccuracy to your solutions. So for example, the longest, for example, here is what we call bad aspect ratio, when you have a long to the short, the aspect ratio is the largest dimension to the shortest dimensions. So this type of element, you have a very high aspect ratio compared to this one, then probably in terms of accuracy, this is not that close to our actual solutions compared to this type. So if you can see this graph itself, if you have an aspect ratio of 24, okay, where you have the elements of a very long and what we call slenders, compared to what we call a rectangle type of what we call element itself, where your aspect ratio is 1.1. So if you look at that, your errors compared to the exact solution, it could be from 1.1, probably you have a 5% errors, then compared to the exact solution. But if your aspect ratio is go up to 24, then yeah, you will see that your percentage error is about negative 55%. So take note on basically the meshing or discretization in terms of aspect ratio would help in our approximations in this case. Then of course, that is one of the parts. I mean, under finite element modeling, we say that yeah, we want to go as close as the physical behavior of the actual problems. Then the discretization is one of it lah. So in terms of meshing, we have to take note on that. The second one is in terms of computation costs. Okay, so if you under two-dimensional, right? So if your problems is symmetrical, okay, your models to analyze is symmetrical. So probably we can make use of this symmetry features, okay, of the structure, so we can greatly reduce the computational time or cost lah, in this case. So if you model is symmetric, then probably your model size can be cut half. So basically, you just analyze half of it in that case, then you can improve your computation time by half, or using under the same computation time with when you analyze the full, okay, you are allowed or you are more affordable to go into a final discretization, meaning a smaller mesh size for better accuracies of approximations. So that basically it would help more, okay, in terms of either you want to go for computation times or accuracy. If you have a symmetric model, so always look for symmetrical basically analysis. So a structure possesses symmetry if its component are arranged in a periodic or reflective manners. So in the case of symmetries, so reflective if it's just like a mirror types. So in this is the case, then probably you analyze one side of it, then probably you can basically they process the same results if you are putting analyzing the both. The other one is axis symmetry. So this is like what we have discussed. So if you have a cylinder type axis symmetrical along along the cylinder center line, then whatever load that you apply, okay, over that particular three-dimensional cylinder could be translate into a two-dimensional problems lah. Or here, it's talking about axis symmetry check bodies in this case. So another type of symmetry is rotational types, as you see here, and translational types lah, symmetry, as you see here, right? Or could be any combinations. So in symmetry, okay, property can be applied. So the reason or the advantages are it reduces the problems, the size of the problem, and you can save CPU time, disk space, post-processing effort, and so on. So one of it is computational cost. Then the second one is simplify the modeling task. So you do not need to model the entire full problems. Okay, probably just half of it in this case. Then it can also help us to check our FEM results. Okay, if you know that your problems or your model is symmetrical, so if you solve both, okay, then probably they should give you both sides. Then it should give separately. If you solve separately, then it should give you the what we call the similar result. So basically, it helps us to cross-check back our FEM result. If it's no, then probably it's your model itself or your whatever loading, your meshing is not same, okay, among the two. So basically, it helps us to cross-check back our result. If it's symmetrical, then it should give us the same results. So if you have a proper your structure have a symmetrical property, then it should be fully exploited or retained, okay, in the FE model. So here, two things that we can achieve. One is computation costs, right? The time can be greatly reduced, or you can, or you are allowed, or you are affordable to go into a final discretization in a symmetrical in symmetry models. Okay, you can go into higher accuracies. The second one is in terms of modelings. I mean, either you go for symmetry, then the second part is basically involving maybe your component is not just one component, involving multi-components. So here we call it substructures. So if you dealing with this type of problems, then basically in terms of substructuring, right, is a process of analyzing a large structure as a collection of components. So you can basically split them into a component and analyze in components rather than the entire full assembly or full as complex structures, a large model. Okay, so basically this substructure basically is just simply your finite element models of a portion of your structures. So in this case, probably instead of this load itself, this box itself, together with the frames, together with the base view itself, it could be probably analyzed separately. Right? Then it will save. In this case, could be saving your times in model, basically in terms of analyzing the full complex large models. So the advantages of using substructure technique are good for large problems. So if you have a very large models problem, then sometimes if you have exceeded your computer capabilities, okay, then it cannot complete. Okay, it's too large, too heavy. Then probably you can analyze by parts or by components. So in this case, you will have less CPU time per runs, right? So will be basically save you time and space. So you can model by different group also your each components. Then it allows us to also partial redesign. So if you have a separate component, so in the case of later on in redesign, you want to change your design, that particular component itself you change, then the analysis of that particular component, basically you can only you reanalyze or resimulate again, not involving the entire full large models, right? So so of course it's good for localized problem, or here referring to local non-linearity problems. Okay, if certain problems, certain component or certain problem involving a non-linearity, then probably because you are separating them into components, so probably that component itself you can making use of the non-linear analysis rather than linear analysis to look into it. Okay, so basically the problem can be splitted. I mean, the model or component model itself, large model itself, can be splitted and you can analyze separately. So, right. So it will be good, okay, if you are looking into static deformation and stress analysis. Okay, if you are using subcomponents, so basically they can be separated quite well, basically analyzed separately, individually. But there are the disadvantages also of using this substructuring technique. So you need to manage more files. Okay, each component, maybe you have one files. Okay, so if you have many components, then you have to manage all these files. Then setting up the models, okay, the settings involved. Of course, each component you have their own setting, the loads, the boundary, the meshing, everything you have to reset basically for each component. So increase the initial time. I would say that the processing time will probably reduce, but the initial time or setting up time will be increased. Then probably, okay, it will induce another layer of approximations, because component to component there are also some boundary, okay, some so-called context, right? So basically if you splitted them, then probably you have to do another approximation or assumption of how these loads from one component transfer to that component, how is the boundary between these two components that I have to separately. So that basically induce another type of approximations, especially for dynamics analysis. So here itself, of course, it's good in terms of analysis faster, but then in terms of approximation, probably it will go another layer of approximations. Then then you basically will affect your accuracy if it doesn't really consider correctly on your so-called the boundary, the load that I have mentioned just now. Right. Then that is modeling. Then we just now we said that about the aspect ratio of the meshing. Then of course one of aspect ratio itself of the mesh itself would greatly affect the accuracies. Okay, and the modeling itself could help in terms of computations times. Okay, the cost itself. Then the next will be more towards the meshings. Okay, the refinement of the meshing. So how small or how so-called how many elements I should use. Okay, numbers of elements that I should use, or what is the size of element that I should use. So where we have to find what we call a cut-off point lah. Basically, I would say that where it give, because you increase number of element or you reduce the size of element, it means what? It means you have more elements, means you have a longer computation times. So you have to find a cut-off point, okay, where you can get a relatively very good accuracies in your approximation. At the same time, it won't take your computation time. It won't take like overly taking too long time to complete these things. Okay, so you have to find basically a point that you will basically not compromise on both so-called this particular size, interval accuracy, and the computation times. So sizing of element and mesh refinement. So basically, there are some so-called tips, okay, on this. So if you are looking into more towards a global type of movements or global types of analysis, I mean here talking about probably displacement. Okay, so if you're analyzing on displacement, basically the whole structure is moving together, subject to that loading itself. Then probably the meshings, or what we call the mesh sizings, or even uh, the 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 number of element maybe not so we don't need to be so refined. But in the case of you are moving towards a very localized problems like stress, especially you have stress concentration where you always only gather at a certain localized point, then probably at that particular localized point or at the entire problem, you need a better mesh, a smaller or refined mesh, or not more number of elements in this case. So that is one of your considerations. Right. So that is on mesh size. Then in terms of solution, as we have mentioned before, we have direct methods and iterative methods. So of course, both you have these pros and cons. So direct methods, of course, it is based on the time. It is based on the size of the matrix. So with the size of metric and the bandwidth of your matrix itself, of that particular problem itself. So when we talk about the size, we know that the size of metric, let's say this is your K itself, then this is your size, let's say 10 times 10 matrix, right? So the bandwidth is basically is how if you still remember, this is, let's say, diagonal, then this is a this is your bandwidth now. So if this particular part is 0, right, is 0 0, so the non-zero part depends on how how wide is the band or on your metric itself. So if we cover so-called the interactions between your one element to another elements basically. So it's between your interaction between the one element to one element. So if you have a very large bandwidth, then probably the solution time will be larger. So solution time is proportional to the MB squared. So your size of the matrix is the size of your so-called the node itself. Then also with the how the bandwidth is talking about the yeah. So depends on this is one band. Your band is 1, then this is 2, this is 3. So if you have just like this, then the rest are 0, then you have a bandwidth of 1, then will be easier. So meaning to that is your other nodes, I mean your nodes interaction between the latest other nodes is lesser. So it's easier to solve in this case. So greatly depends on that this the size itself. So that's why it's suitable for small or medium problems. So slender structures, then you have a smaller bandwidth. So because the interaction between your nodes is lesser, so you have a smaller bandwidth. So it is also easy to handle the multiple loads cases. So in the case of I want to change loads, I want to change add other load at other node itself. So it's easier because we build the K U equals to F. So always we can change this F if I have involve multiple load. So if I have other nodes, we have to add load itself also can be easily added, then you solve against the whole thing. Okay. So but in the case of iterative, if you still remember that we have shared before, so every time the load itself, it have to be considered and it have to be solved in every iterations. This is your k x or ku equals to f. This is your f itself. So you see that all your f1 f1 let's say f2 f3 are being used for each iterations for one iterations to solve. So in the case of you want to change your load, let's say at here, or multiple load, you want to change add more loads at here at different point, then the whole thing have to be rerun against, and in terms of iterations. So all basically this equation will be all different already. Then solutions wise, for different load cases, iterative you need to solve the system again. So iterative methods solution time is unknown beforehand. So it basically greatly depends on the tolerance that we want, the stopping criteria that we set. Okay, so that the solution time is unknown beforehand. Then storage also storage requirement also reduce greatly from using iterative compared to direct method. So direct method is basically heavier. So iterative methods it basically can be more suitable for large problems. So multi-structure where you have dealing with large bandwidth metrics. Then yeah, so iterative method is more suitable. All right. So in the solutions, basically we have to remember that this FEA model is a mathematical model of a real structures. Is based on many approximations, right? So if you compare back with a real problem or real structures, so real structure is an infinite number of nodes. So continuous systems or infinite number of nodes. So you have an infinite number of degree of freedom. Compared to your FEA models is a finite finite element, right? So you have a finite number of nodes, finite number of degree of freedoms. So here we are saying that because you have a finite number of nodes, therefore finite numbers of degree of freedoms. Okay, so the 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 degree of freedoms for each node itself is finite, is lesser compared to the actual. Okay, so the way meaning the way you restrict the nodes, okay, is in I finite element is larger. So okay, so here we are saying that FEA model is stiffer than the real structures. So if it's stiffer, then your displacement in terms of displacement subject to the similar loads will be lesser in this case. Okay, because of the limited number of nodes and limited number of degree of freedoms. Okay, in our FEA model. So in general, this displacement, if you are talking about displacement results, for finite elements, okay, it is always at the lower bound of our exact solutions. So it's always smaller in magnitude than the exact values, right? So compared to your actual solutions, your finite elements approximation or analysis result is usually lower than the exact solutions. So here, of course, you can go as close as to exact solution by increase the number of degree of freedom here, meaning you increase the number of nodes or number of elements. So if you have a more elements, larger number of nodes, or meaning you have a smaller size of elements, then probably you have a closer approximation compared the exact solutions, right? So if you can see this, the displacement, if you have a lesser degree of freedom or lesser element, lesser of nodes, then you are always at the lower bound. Okay, no matter how many degree of freedoms, okay, you are using, how many numbers, okay, as long as you have finite elements, then you are always at the lower bound of the exact solutions or in terms of displacement. But then if you want to go closer, then probably you have to increase the number of elements. Okay, so we have several type of refinements here to probably go as close as the actual or exact problem solutions. So we have the names. So few way we can do it. Either we reduce the size of elements, means we increase the number of the elements. So we reduce the size of elements. So here we call it H refinements. So we want to refine, or we want to improve our accuracy through the refinements of the size of the elements. So another type is a P refinement. So what other things that we can do? Okay, besides increase the number of element or reduce the size of the element, right? So we can also increase the what we call the orders, right? Increase the orders of our so-called our functions, right? From linear to quadratics. So if you are at a higher order, then probably you are at higher accuracies. You have a better accuracy in this case. So in this particular refinement, if you are using higher orders, so-called functions or polynomial function here, from linear to quadratics, also you are actually increasing its accuracies in terms of its polynomial functions. So here we call it P refinements. R refinement is more towards rearrange the nodes, okay, in the mesh. Okay, so like I mentioned, okay, these are refinements, rearrange a node in the mesh. Of course, it will help uh, in helping the solutions in terms of the solutions time. It will help in terms of the solution time, in terms of your accuracies. Okay, also probably not that much. Okay, but yeah, in terms of like what I mentioned to you, the aspect ratio types of elements, then you rearrange it, then probably you can avoid all these large aspect ratios kind of problems, okay, that you that probably will what we call induce inaccuracies. HB refinement is more towards combination of your size, okay, reducing the size of element and also the the higher orders. Okay, so combining H refinement and P refinements. So in ANSYS, we can have, okay, we can change the size of our elements, reduce the size of element to increase the accuracy. We also it also allow us to change between linear and quadratics. So if we want to go for quadratic, then we can basically we are looking into a P refinement in this case. So with any of these refinements types, so your solution will converge to basically the solution, analytical solution of your mathematical model. So basically, under iterative methods, I mean, especially in ANSYS, you are under iterative method, then basically it will, based on this so-called the refinement that you have set, so it will try to converge and stop, right, and give you a more accurate result in this case. So some software also you have this automated automated kind of refinement processor. So here we call it adaptive meshing or adaptive solutions. So later on in our examples, I mean, you can see that we also making use of this adaptive meshings, okay, to help us to refine. Basically, it's more towards H refinement, reducing the size of element to get a better, what we call a more accurate result. Okay, so in terms of the results, so what we are doing here is basically we have to set a criteria, the stopping criteria, the what we call the tolerance that we want to achieve. Then it helps us to refine, okay, in terms of the size until it fulfill the achieve the what we call the tolerance of the requirement that we have set. So then you get at least a more reliable results. So in terms of manual types, this is adaptive, is a more automated one. Manual type, so usually we, if you are performing a computational analysis, what we call the finite element analysis, so usually you are required to do this kind of refinements to basically, like I mentioned to you, find a cutoff point between your the number of size, the number of element or the size of the element that you want to use to achieve a relatively good accuracy, as well as not too, I mean, in terms of computation time also is relatively reasonable. So that is what we call mesh independency test, where you play around, same like adaptive. Adaptive is basically automatically help you to reduce the size. Then you find what we call the suitable meshings that can converge, okay, and give you a relatively good reliable result. So mesh independency test also similar like this adaptive meshings, but then you have to do it manually. Okay, what you can do is basically you change the mesh size, okay, or your whatever, how you mesh it. So the meshings or the mesh in terms of sizing, or in terms of the way it arranged, or in terms of its the orders. Okay, so you have to change it until you get your consistent your results in terms of let's say you are looking into displacement, your result. Okay, you may probably you start with let's say a size of 0.2 mm, then you slowly reduce the size. Okay, you get the higher accuracies, right? You reduce the size until the changes of between the subsequent two tests, okay, is achieving a tolerance that you set. So then that consider a good mesh result that basically we are say that it give you a considerably very good accuracy at the same time. you have a particularly good computation times. So what we are doing, I mean, in that case, usually there is you can do. So usually you play around with let's say I'm using stress is my mesh. Let's say I play around with my stress level. Okay, then I play around with my mesh size of 0.5. Then I get a value of uh, let's say 16.34 megapascal, right? Then I try to reduce it because I want better. We know that refine the mesh size will basically help us to improve our accuracy. So we try to reduce it. Okay, let's say 0.25. Then we get around 14. Let's say 14. Uh, uh, 5 megapascal, right? So you can see that there is a change of 16, let's say, to 14. So you see that the approximations it changed to a lot. So meaning to that your originally or your 0.5 mm of size of meshing is maybe not so accurate in this case because you see it is still greatly affected by the size of your mesh, okay, your elements. So if I try to reduce to 1.125, then probably I will get if lah I will get 13.4. So if I further reduce to point 0 75, let's say uh, 0.625, then probably I will get 13.3. Okay, then we can say that this itself is a good mesh size in this case, right? Because you going down to a smaller size, it doesn't really change it. So we can say that this particular mesh size give a relatively good or reliable results in this case. So mean to that if you go smaller size, mesh size, probably it won't help in terms of it won't change much in terms of its the accuracies. So then we have to use this size in term instead of maybe a 0.5. Maybe it's too large and the changes is too much. Still a lot of changes when you play around with the size. So still very dependent on the sizing, right? So that is what we call mesh independence test. So later on, adaptive solutions, adaptive meshing in our example is kind of this around these things, but then it design automatically. So we will look into it in the example later on. Right. So in terms of types in ANSYS meshing, and if under 2D, if you later on try the examples, I mean the case study itself. So probably is you are in 2D, okay? So you have to choose in your analysis is two-dimensional. Then only you will see the mesh type of two-dimensional elements So what we have learned, the triangular, the quadrilaterals, then it will come out. If you are choosing three-dimensional analysis, then you will see the three-dimensional types of elements. So this basically is the layer in terms of your meshing. So first, you're talking about the physics and meshing methods. Then you have a global setting and localized or local mesh settings. So usually, what we have done previously in our previous example case studies are all global settings. So we set our mesh size global in the global setting. I want default, I want 0.2, I want 0.5. So that is on under global. So if you want to go for local setting, then you have to call a separate so-called mesh setting, size setting to basically probably you can assign to a certain phase, you want this size, another phase, you want this size. Okay, so that is a more towards localized or local setting. So under physics preferences, of course, you choose mechanical. We are dealing with solids, right? Under mechanical, the meshing method. If you are in 2D bodies, then you will 2D analysis. You will see this type of the elements are quadrilateral dominance, triangular. Then you have this. Basically, it's these two types like quadrilateral and triangular, right? So both of them, okay. Of course, you can use. You see that the type that you after the type that you have the method that you have choose. So you have auto. Of course, you can choose auto. You can have quadrilateral. You can triangular, uniform, quadrilateral, or triangular, or uniform quad. So these are the types of what we call the matching method that you have uh, if you are in 2D analysis. So at the same times, okay, under this method, you have this what we call element mid-side nodes. So in the old versions, okay, if you are using an ANSYS old version, then you will see this element mid-side nodes. So this element mid-side nodes basically is talking about the P refinements. So is it linear? Is it quadratics you want to use? So if it drops, then meaning you are dropping the elements mid-side nodes, meaning it's a linear functions or you are using. So if you put cap, then probably you are looking for P refinement or higher orders, or here is a quadratics functions. So under the new versions of ANSYS, basically you won't see this, but it's basically tell you the orders, linear, or you can choose from either the global setting or in under this here global setting, you will see orders. You are setting linear, auto, or basically quadratics. Okay, it doesn't use drop and cap anymore. But then if you're using O1, then basically to let you understand this drop means linear, cap means quadratics, right? Then this is how it look like lah. So if you are putting drops, then basically your elements don't have a mid-side node. Then here is talking about linear functions or orders, okay, the first order. Then if you're putting cap, then basically every basically between two nodes you have one mid-side nodes. Of course, you won't see it, sorry, in the actual so-called meshing, but then basically it will consider that is another nodes, right, in your so-called mesh. Okay, so that is the mid-side node, or what we call the P refinements that you can use. All right.